This video discusses a specialized version of adding carbanions to carbonyls, which is called the Wittig reaction, and it's named after the chemist who discovered it. This reaction requires a fancy carbon nucleophile called an ylid. We'll start with 2 steps to make the ylid, and then we'll discuss how it reacts with aldehydes and ketones. Here in the summary scheme, I have shown an aldehyde reacting with a non-stabilized ylid to form a cis olefin. We'll also talk about stabilized ylids and how they form trans olefins, and the Horner-Wadsworth-Emmons reaction, which uses a stabilized phosphonoester or phosphonoketone ylid and results in the formation of trans olefins. We make a phosphonium ylid from a phosphonium halide, and so first we need to talk about how we're going to make a phosphonium halide. So we can simply make this from an alkyl halide, and this reaction is a simple SN2 mechanism with a phosphine nucleophile. A phosphine is a phosphorus reagent with a lone pair and 3 alkyl or aryl substituents. Here I've shown triphenylphosphine. So the lone pair on the phosphorus is nucleophilic, and it can do a backside attack on an alkyl halide to form a phosphonium salt. This salt is then used in the Wittig reaction along with the strong base. The strong base is what will form the ylid, and that's what we're going to talk about on the next slide. In the Wittig reaction, the active reagent is formed by deprotonation, and then this carbonyl starting material is added. The position next to phosphorus can be deprotonated by the very strong base N-butyllithium because the resulting anion is stabilized somewhat by the positively charged phosphorus. The result is an ylid, a name we use for any molecule that has a positively charged atom right next to a negatively charged atom. Because the positive charge is on phosphorus, we refer to these as phosphonium ylids. Remember that phosphorus is in row 3 of the periodic table and can support more bonds than row 2 elements. We can see that in the resonance picture, we have 5 bonds to phosphorus. Finally, we've come to the Wittig reaction itself. It starts like any other carbanion adding to an aldehyde or ketone to form a tetrahedral intermediate, which in this case we call a beta-ene. The aldehyde and the ylid will approach with their R groups as far away from each other as possible, leading to the intermediate that I've shown here. Because phosphorus and oxygen love to make bonds together, the molecule quickly rotates until it can make a PO bond to form an oxyphosphatane intermediate. When non-stabilized ylids are used, this will result in a syn relationship between the R group on the aldehyde and the R group on the ylid. There's a strong driving force for the formation of a phosphorus-oxygen double bond. Thus, the 4-membered ring collapses to form 2 pi bonds in a process called a retro 2+2 cycloaddition. The final result is a cis olefin and triphenylphosphine oxide. Note that the formation of this PO double bond is the driving force for this reaction because the bond is so strong it provides the reason that the reaction becomes exothermic. The previous example involved an ylid with an R group that cannot stabilize the negative charge on carbon. This ylid is referred to as a non-stabilized ylid. These react through a pathway that leads to the cis olefin. By contrast, stabilized ylids lead to trans olefins because the carbanion addition becomes reversible, which allows for the formation of the thermodynamic product. Here, I'm going to draw a few example non-stabilized ylids for you. After that, we'll draw some stabilized ylids, and we'll see how the anion part of the ylid can be stabilized by resonance. So here I've shown an example where we have a phenyl substituted ylid, and as you can see, the negative charge can be distributed all around the aromatic ring. This increases the stability of the ylid enough to allow it to be added reversibly to the carbonyl containing compound. So in this case, you'll end up with a trans-olefin. The Horner-Wadsworth-Emmons reaction proceeds by a nearly identical mechanism, but it involves a phosphonoester or phosphonoketone ylid. Let's look first at how to make these starting materials. We can build the phosphonoester or ketone from a phosphite and an alpha haloketone. The phosphite is usually trimethylphosphite. In this case, we're going to react with an alpha bromoester to form a phosphonoester. You could also use an alpha bromoketone, where this here would be just a regular R group, and that would lead to the phosphonoketone. The phosphorus lone pair will start by attacking the alpha bromoketone in an SN2 pathway. Next, the bromide attacks one of the methyl groups on the phosphonoester and the phosphonoester itself is quite an outstanding leaving group. Remember, the PO bond is very strong, so there's a strong driving force for this group to leave. The result of this process is the desired phosphonoester. Overall, this transformation is called the Arbuzov reaction. Now that we've synthesized the necessary ylid precursor, we can look at how the ylid is formed and how the HWE reaction occurs. Because the phosphoryl group, the PO double bond, and the carbonyl are both inductively withdrawing and both resonance withdrawing, the hydrogens at the carbon between them are fairly acidic. We don't need the super strong butyllithium here, and instead, sodium hydride is typically used. We start this reaction by deprotonating to form the ylid. Next, the carbanion adds to the carbonyl in a reversible step. Formation of the PO single bond leads to a beta-ene intermediate. And then the same retro 2+2 process will provide the final product, which will be a trans-olefin. That covers the new mechanisms for today, and now we'll take a look at a synthesis problem. Here you're asked to propose a synthesis of the below molecule from any starting material containing 4 or fewer carbons. Please note that your reagents can have more carbons than 4 if the carbons in the reagent do not end up in the target molecule. So for example, you could use potassium terbutoxide to deprotonate a hydrogen, but the terbutyl group does not end up in your target molecule. You actually now know 2 reactions that can produce this molecule depending where you disconnect it. What I mean by disconnect is to pretend to break the bonds. So what we're going to do is a process called retrosynthesis. Retrosynthesis is the process of deconstructing a target molecule into readily available starting materials by means of imaginary breaking of bonds, which are called disconnections, and the conversion of one functional group into another, which are functional group interconversions. So since we just learned to form a double bond from two molecules, let's look at possibly breaking this bond here. So I'm going to use this little line symbol with the balls on the ends to mean this is where I'm going to pretend to just cut the molecule. When we make such a maneuver, we use a special kind of arrow called a retrosynthesis arrow. We do not use a normal reaction arrow here, and we do not use this arrow for any other process in organic chemistry. So to do a Wittig reaction, we would need to have one carbonyl compound and one ylide. So there's two ways you can do this disconnection. The first is shown here, and that would involve starting from acetone, which is a readily available and inexpensive reagent, and this ylide, which I think is actually the phosphonium halide precursor, is commercially available. So if we're going to think about how we access this ylide, we know we need to make that from the triphenylphosphonium bromide. And that in turn is made from the corresponding alkyl halide and triphenylphosphine. Okay, so that's how we would start the synthesis, is with this alkyl bromide here and acetone. And so we would first have to make our phosphonium halide salt and then use a base to deprotonate to get to the ylide. Another way you could imagine doing the same disconnection is to switch which side has the carbonyl and which side has the ylide. So both of these pathways would be acceptable answers, although given the fact that acetone is much cheaper than butanol and the ylide for that pathway is accessible from the deprotonation of a commercially available phosphonium halide, that would seem to be the more practical path. Now, if we take another step back, we can look at the other way that you already know to build this molecule using Chapter 15 chemistry. And that is to break the molecule here. And if you were to do that, you would use a Gilman coupling reaction from a vinylic halide and the corresponding propyl cuprate.